Hello, I'm Mehmet Emre. I'm here to present our paper Translating C to Safer Rust in Splash 21 UPSLA. And this is joint work with Ryan Schroeder, Kyle Dewey, and Ben Hardikoff. So our paper is laid out in two big ideas. On first, identifying the cause of unsafety in Rust programs translated from C, then starting to fix these issues. So my talk will be outlined in motivating our problem than talking about these two issues. C and C++ do not guarantee memory or thread safety. They are used because they allow precise control of resources such as memory, but this precise control comes at a cost. They can introduce subtle bugs. For example, in the first half of 2021, there was on average about one buffer overflow vulnerability per day on the common vulnerability and exploits database. This includes a vulnerability in sudo and 20 vulnerabilities in Chrome. Rust is an alternative to C and C++ that provides a ergonomic low-level programming language where the compiler checks use after free and data erase issues statically. And it's being adopted by commonly used C and C++ projects such as the Linux kernel, Firefox and Chromium, curl, and Android. And a lot of infrastructure software is still in C. Like all of these are still C and C++ projects, and there's many more. And there's some effort from the industry to translate C into some unsafe Rust. And the state of the art that we know of here is C to Rust. Here the idea is to get some unsafe Rust code that mimics the C program exactly the same. Then let the programmer rewrite the program bit by bit or use some refactoring, so that the programmer is responsible for the error-prone task of adding the safety annotations or changing the program while preserving the semantics. And our ultimate goal is to automate this process and translate this program to a safe Rust program. And this paper is a first step towards that goal. Our contributions are a study of unsafe Rust programs translated from C, and we classify a cause of unsafety to understand what to do for making these programs safe. After knowing what to do, we started with a specific category and fixed the issues with that cause of unsafety. Now let's look at causes of unsafety in these Rust programs. So based on our analysis of the programs translated from C and looking at the definition of unsafety in the Rust manual, we categorized 6 causes of unsafety that we observe in these programs. 4 of these are caused by lack of C's language features, and the remaining 2 are caused by external code that the compiler cannot reason about, and the ones that are in bold are more common than the others, and the detailed numbers are in our paper. So let's look at each of these causes. So if we have unsafe pointers because the C program doesn't have any lifetime or array bound information, you may do unchecked pointer arithmetic or have dangling pointers that we dereference, so that is a reason that the program is unsafe. And if we have mutable globals, then we can cause data erases by accessing the global from multiple different threads. And units and unsafe casts cause the same issue. They both allow reinterpreting a piece of memory as a different type. And if we are calling into external functions or using inline assembly, that's some code that the compiler cannot see or cannot reason about. So these can't do anything in the previous items, therefore they are unsafe. And with these definitions at hand, we collected 17 open source programs from several application domains, including algorithms, I/O, file format parsers, neural nets, and 10 of these come from C to Rust's own manual, and the remaining 7 come from GitHub. So we have a wide variety of size and application domain in our corpus. So looking at all of our corpus, we counted how much each behavior occurs and how many functions each behavior affects. And we use a different counting methodology than existing papers that focus on quantifying unsafety in general Rust programs. In existing work, the most common cause is calling another unsafe function, but that's not helpful for us because we want to essentially answer the question, if I fix a cause like external calls, how many functions in my program can I make safe? And to answer that, we essentially count the same behavior for the function that it occurs in and all the transitive callers. For example, in this call graph, cooks makes an external call, so foo, baz, and cooks are all three marked as unsafe because of external call. Similarly, baz makes a row pointer dereference, so foo and baz are both marked as unsafe because of that reason. And with this counting scheme, we observe that most functions are unsafe because of multiple reasons. And when we look at singular reasons, unsafe pointers are the biggest cause. 15% of the functions were unsafe because of unsafe pointers. And now let's look at unsafe pointers, the biggest cause. We have unsafe or raw pointers because of 4 reasons in these programs. Either there's a lack of lifetime information, so we don't know whether a pointer points to a valid object, or there's some pointer arithmetic and we don't know the bounds, so we don't know whether we are pointing a random piece of memory. Then there's void pointers, which allow stripping types, so they're raw, and that's caused by C's lack of generics. And finally, external APIs may use void pointers or other raw pointers. And overall, we observe that most pointers are affected by multiple causes. And when I say multiple, I mean a combination of 2, 3, and 4, because at the end, all raw pointers are raw because there's no lifetime information attached in the first place. And when we look at each cause in isolation, the most common cause is lack of lifetimes. The rest of our paper focuses on fixing pointers that are unsafe because of lack of lifetime information. So we try to derive lifetime and ownership. So let's look at first what lifetime constraints and ownership constraints Rust checks. From Rust point of view, each object has a statically checked redirect lock of sorts. So throughout an object's lifetime, each object has only one mutator or it has many readers, but we cannot have both of them together or multiple mutators. This is not allowed, for example. There cannot be a reference that outlives the object it refers to, so that's how the compiler disallows use after free. Here in the snippet, y is a reference to x, and y's lifetime doesn't extend x's, so this is okay. But if we were to return y in this case, then scope of y is now longer than scope of x. So this is no longer okay because y outlives x, and this may cause a use after free bug. And the compiler computes all of this information inside the function. So we need to annotate only the function signatures and type signatures to aid the compiler. And inside function bodies, we need to tell the compiler when we are borrowing an object or when we are moving ownership. So with all of this in mind, our goal is to keep the same semantics as the C program, do a very low level rewrite. We are not trying to come up with a new algorithm to replace an existing algorithm that's implemented in the program. And we are trying to prove existing safety to the Rust compiler. So we start with an initial program where we assume all pointers are borrowing, all sharing is okay, and we have unique lifetimes everywhere. Then because this program is very optimistically annotated, it will have some program errors. Then we'll use the compiler as an oracle to fix these compilers and find the borrow checker violations and add necessary annotations to the program to constrain it and test the compiler. And we iterate this process until we get a compiling program. And before all this, we also do some pre-processing, and the details for that are in the paper. So when we are writing the program, now we have 3 main bits to rewrite: function bodies, type signatures, and function signatures. So let's look at this program. So this is a hypothetical Rust program translated from C. We have an object that's created and returned by create tree. Then we save its address in this pointer tree. Then we use that pointer later on. So let's do our initial rewrite. And we just say, okay, everything is borrowing. So we borrow the object returned by create tree. And then that value is used later on through that pointer in purple. The value flowing to tree needs to live throughout this scope because it's being used in multiple places there. However, because it's a temporary object, it's going to be deallocated at the end of first line. So we need to make the purple tree an owned pointer so that the object it references to is going to be alive throughout its lifetime. And we transfer the object's ownership rather than borrowing in this case, and the value now lives long enough. The next problem we are trying to solve is figuring out the struct field lifetimes and struct lifetime parameters. There might be a complex points to graph between structs in a program, like the one shown here. And some of these fields will form cycles, so we cannot assign unique lifetimes to all fields. So we do the next best thing and we create the graph of string, the connected components of this points to graph. And we assign a unique lifetime to each edge in that graph. For example, in that graph, s4.bar and s4.foo will both have the red lifetime. And we guarantee that we will have only finitely many lifetime parameters for each struct. Now that we figured out how to annotate function bodies and struct signatures, the last remaining bit is function signatures. So we start with unique lifetimes optimistically. This is similar to how we annotated function bodies. Then we use the compiler as an oracle again to find necessary constraints to add to the function signature. So we start with this function signature where we do not have any lifetime information. So the compiler cannot reason about this and it would complain. So we add unique lifetimes to all the holes in this function signature. And now the compiler would look at the function body and say it cannot satisfy this signature because of certain constraints not being met in the function signature. So we add the necessary annotations based on the constraints derived from the compiler errors. And to put it all together, we use what we call configurations as a representative of specific constraints we got from the compiler. So we run the compiler, we got some errors, and based on that, we need to keep track of what modifications we are making to the program. We keep track of the set of lifetime constraints we figured out, and we also keep track of different pointer kinds for each pointer. We start by borrowed pointers and define a lattice climbing up to owned and row pointers. We process error messages to get this information and promote pointers when necessary. For example, we promoted the tree pointer from borrowed to owned in our example. So we get a larger configuration in each iteration, and we have a finite lattice here because the number of pointers are finite and the number of lifetimes in the program are also finite. So we guarantee termination. And we also set the lattice up so that the maximal element is the one where all pointers are row. So it's going to correspond to the original program. We guarantee to get, in the worst case, the original program back. We observe that for the pointers that we were trying to fix, specifically the ones that are unsafe because of lack of lifetime information, we make 76% of those safe and 89% of the references of these pointers safe. So we fix most of these pointers. However, when we look at the larger picture, we fix only 8% of all pointers because most pointers were unsafe because of multiple reasons. When we looked at our benchmark programs, we noticed we could not make some pointers safe because they are not used safely according to the borrow checker. The C programs do not have a notion of what the Rust borrow checker expects. And we give an example of this in the paper. The most common cause is having two mutable borrows that are alive at the same time. For example, mutably borrowing a pointer, then reusing the original pointer to make some mutation while the first borrow is alive. And in 3 of our programs, there were some function pointers, and we kept the signatures of function pointers intact because some external functions could flow into function pointers. Our tool needs to be run only once because we need to run it only when we translate a program from C to Rust. Most of our programs, including some of the ones that are on the order of 100,000 lines of code, took less than 2 minutes to go through all of our technique. However, libxml2, our largest benchmark, took 125 minutes. And this is mainly because they are large stacks with many lifetime constraints. So we had to discover a lot of lifetime constraints bit by bit. And most of this time is also spent on taint analyses we use to propagate solutions to compiler errors. These analyses are used for figuring out if an object is owned, then all the values flowing into that object also need to be owned, and propagating the ownness property. Thank you for listening to my talk.